Hello everybody and welcome to the minimum distance to every vertex coding question. We are given a directed graph with n nodes labeled from 0 to n-1 and we should compute the minimum distance from the source vertex, which in our case is 0, to every other vertex in the graph. This is a classical problem that involves the breadth first search algorithm, or in short the BFS. And I'm going to show you how it works right here. BFS, just like DFS, is an algorithm designed to traverse all the vertices of some graph. But BFS is iterative, and as the name suggests, it traverses the vertices by the breadth or by the width instead of the depth, which is more appropriate for minimum distances or minimum paths problems. Let me show you how the algorithm works. We are going to use the queue data structure. We will have a queue in which we will initially push the source node, which is 0. We will also use an extra array, minDist, where minDist of some vertex v denotes the minimum distance between the source node 0 and that vertex v. Initially, we will fill this array with values of -1, denoting that we haven't reached any node yet. But minDist of the source node, which is 0, will be initialized at 0 because the minimum path between 0 and 0 is of course of length 0. This algorithm will run for as long as the queue is not empty. We will write code in a minute, but basically we will have a while loop checking that the queue is not empty, and inside that loop, for as long as this happens, we will select the node in the front of the queue, basically the leftmost one, and then we will loop over its neighbors. And for each neighbor, we will check if it has never been visited before, or in other words, if minDist of that vertex is -1, and if that's the case, we just found the minimum path from the source to that vertex, so we will update its minDist and we will push it into the queue. So, for vertex 0, of course, we won't know the order in which we will have these neighbors in the adjacency list. Let's suppose 1 was the first neighbor. We will check, has vertex 1 been visited before? No, it hasn't. Its minimum distance is -1. Okay, so we just found the shortest path from the source to this vertex, and the distance of this path is equal to the distance of the shortest path between the source node and this node that we selected, the node that we are coming from, plus 1, of course, from this edge. So what we are going to do is update the minimum distance with value 1, and then we are going to push this node 1 into the queue. We can also write down the minimum distances right here at the vertices as we find them. It's easier to see. And now check this out. We will not continue the algorithm from vertex number 1 and basically loop over its neighbors and extend there and loop over their neighbors and so on and so forth. This is what the DFS does, and that's why it's called depth first search, because you are basically going in depth, in depth, in depth with recursive calls. But now we will go by breadth, which means that we have this node 0 and we are going to extend to all of its neighbors first, and then we are going to continue the work from those neighbors. So we are still at node 0, we looped over the first neighbor, then let's suppose the next one is node 2. Has 2 been visited yet? No, its minimum distance is -1. Okay, so the distance from the source to that node is equal to the distance from the source to the node we are coming from, which is minDist of 0, which is 0 plus 1. So minDist of 2 will now be 1, and we will push the vertex 2 into our queue. We can also draw this one right here, and then we will still continue from vertex 0 because there is one more neighbor left, which is node 3. Has 3 been visited yet? No, because its minDist is -1. Okay, so we will assign minDist of 0 plus 1 to minDist of 3. This is going to become 1. And we will push 3 into the queue. We can also write this one here. And only now we are done with node 0, we've extended to all of its neighbors, updated their min distances and pushed them into the queue. So now I'm going to pop this node out of the queue and I will continue my algorithm. I am going to check again inside the while loop that I've told you if the queue is not empty, and it's obviously not. So I'm gonna select the node in front of the queue, which is node 1, and I am going to loop over its neighbors. As you can see, because this graph is directed, node 1 has no neighbors, so basically the job is done. Right here, we are done with this node, we are gonna pop it out of the queue. Then, is the queue not empty? Yeah, it's not empty. Okay, let's select the new node in front of the queue, which is node 2. We will loop over its neighbors, and as you can see, it has a neighbor which is vertex 1. Has 1 been visited before? Yes, it has. Its minimum distance is 1. So we are not going to do anything. If a neighbor has been visited before, it means that we have already found the shortest path from the source node to that node, and so the min dist has the accurate value and also that vertex was pushed into the queue. I won't do this again, and if you check it out on this example, I shouldn't do this again, because 1 was visited and I've basically found this path from the source to node 1, which has a length of 1. And now, at this step, when I'm coming from node 2, what I've basically found is this path, 0, 2, and then 2, 1, which has a length of 1, which is greater or worse than the first path that we have found to node 1. This is a super important property of the BFS algorithm, and that is that whenever we visit a node for the first time, we will know for a fact that the path that led us to that node, the path from the source node, from where we started, this was the first node in the queue, and we extended until we reached that node, that path is the minimum one, 100%. And this is exactly why you will see in the algorithm when we write the code, I'm going to only check if the minimum dist is -1, and if so, set it to its new value. I'm not going to check whether the minimum dist is greater than the distance that we have found at this path, because I'm gonna know that for a fact. So let's move on. I'm still at vertex 2. I looped over neighbor 1, it was visited, this is a worse path, I'm not gonna do anything, and as you can see 2 has no more neighbors left. So now we finish the job for vertex 2, we will pop out of the queue. Then we will continue. The queue is still not empty and we will select the node in front of the queue, which is free. We will loop over its neighbors, it has 1, which is vertex 4. Has 4 been visited yet? No, it hasn't. Minimum distance is -1. Okay, so minimum distance of this vertex 4 will be assigned value minimum distance of vertex 3, the node we come from, plus 1 from this edge. So we will have 1 plus 1, minimum distance of 4 is going to be assigned value 2. Let's write it down here. And now that I've just found the minimum path to this node, I am going to push it into the queue because in the future I'll want to maybe extend this path to other nodes. Very well, 3 has no neighbors left, we are done with it, we will pop it, the queue is still not empty, we will select the node in front of the queue, which is 4. We will loop over its neighbors. As you can see, one of them is vertex 2. Has 2 been visited yet? Yes, it has. Okay, so I'm not going to do anything because this path that will come from node 4 is going to be worse than the path I found in the past, and indeed it is. This path would have had length 2 plus 1, it would have been 0, 3, 3, 4, 4, 2, but as you can see I already have a path of length 1, which is directly 0, 2. So no work to be done here, very well. Another neighbor is vertex 5, which hasn't been visited yet, so I'm going to take min dist of 4, which is 2, add 1 to it and assign this 3 to min dist of 5. Let's write this down. I'm gonna have a 3 right here, and now I'm also going to push 5 into the queue. And then I'm not done with 4, it has one more neighbor, which is 6. 6 hasn't been visited yet, so I'm gonna assign this 2 plus 1, distance 3. This is going to be min dist of 6. And I'm also going to push node 6 into the queue. Now I'm done with node 4, I'm going to pop it out, the queue is still not empty, I'm selecting the first node, which is 5, I'm looping over its neighbors, I find neighbor 6, which has been visited yet, so I won't do anything. Again, you can see that the path from 0 to 6 that we have found before has a length of 3, and it's this one, 0, 3, 3, 4, 4, 6, which is better than what we find now coming from node 5, which would have a length of 3 plus 1, it would be 4, and it would be 0, 3, 3, 4, 4, 5, and 5, 6. So as you can see, the property holds true. With the BFS algorithm, whenever we visit a node for the first time, we know that we did so from the shortest path. Very well. So this was it. 5 has no more neighbors, we are done with it, the queue is not empty, we still have 6, we select it, we see only one neighbor, 7, this hasn't been visited yet, so its minimum distance will become 3 plus 1, which is going to be 4, and I'm going to push it into the queue, and I'm done with 6, the queue is not empty, I'll select 7, which has no neighbors, I'm done with 7, and now the queue is empty, the algorithm is over, and we have our answer in the minimum dist array. And obviously, if there were more nodes, for example this 8, which we couldn't get to starting from the source node, because we initialized min dist with -1, those values would be -1, which is exactly what the problem asks. Now that we know how this algorithm operates, what I'm going to tell you is that its time complexity is equal to big O of n plus m, where n is the number of vertices and m is the number of edges. And that is because every single node is going to be pushed into the queue exactly once, as you have seen, and popped out of the queue exactly once, and also every single edge is going to be traversed once. And that will be when the starting node of that edge is the one selected from the queue, the one in front of the queue, and then we traverse the edge in order to possibly extend to its neighbor. That's it, because as I said, each node is pushed into the queue and popped out of the queue only once, every single edge will be traversed only once. The extra space complexity used by this algorithm will be big O of n, the number of vertices, because in our queue we will push n vertices and also we will have the min dist array. Now let's write the code. Here is our function, we have n, the number of vertices, and edges, which will be a two-dimensional array where each item represents a unidirectional edge. And so the first thing we will do is create the adjacency lists based on the edges array, because we want to traverse the neighbors of each node super fast and not loop over the whole edges array. So let's do that. I can have graph, you know this, we've done this for the previous problems. This is going to be a default dictionary where all the values are going to be lists or lists of integers. Then we will loop over each edge in edges, and what we will do is say graph of edge of 0 dot append edge of 1, because as I said, it's only one direction. And then we'll write the BFS algorithm. We will create our queue, which will be a deck object, and then for as long as this queue is not empty, we are going to select the node in front of the queue. So we can say node is queue.popLeft. So we get its value, we store it in the variable node, and we will also pop it out of the queue. Now we will traverse the neighbors. We can say neighbor or maybe adjacent node in the graph of node list. We will check if this adjacent node hasn't been visited yet, which means that its minimum distance should be equal to -1. And so let's also create the minimum distance array first. It will consist of n values of -1, so that's it, perfect. If this is -1, then the minimum distance of this adjacent node is going to be assigned the minimum distance of our node plus 1. And also we will append or push this node into our queue. So queue.append adjacent node. And that's about it. All we have to do is when the while loop terminates, return the minimum distances array, And now we should also import the deck and the default dict objects. I think both of them are from collections. So let's see, from collections, import default dict, okay, and deck, perfect. Very well, now let's call this function find minimum distances for our example that we have drawn. So let me write the example. Okie dokie, that was it. We had 8 vertices and these are the edges in the form of a two-dimensional array. Let's run the code and we have only -1s. This is interesting. Oh, of course, we never appended the source node, which is 0, into our queue in the first place, and also we should have initialized min_dist of 0 to 0. So let's do that. Min_dist of 0 is going to be 0, and also I think I can write 0 directly into the constructor. No, I cannot. Okay, maybe an array that consists of 0, that might work, and it does. Yeah, and all the distances are correct, exactly the ones that we came up with when dry running on paper. Okay, so this is the final algorithm, super short and simple, I love it. If we were to analyze the time complexity, we already did that, but you can see that this is constant. This is big O of m because we loop over the edges. Then accessing that value of edge of 0 key is constant because we have a default dictionary. Appending is constant, all good. This is constant. This is going to be big O of n. We create a list of n items. This is constant. Then we have this while loop, which, as I've already explained to you in the drawing, it will make n iterations, or at most n, because maybe we're not gonna be able to visit all the nodes. Some of them are not accessible from the source node. Then of course this is constant. Then here we are looping over the edges that start at node. So this is going to be big O of number of edges. But as I've told you, we do not think about the worst case and say that, hey, this is at most big O of m, at most m edges in the worst case from a node, which is correct. And so I'm gonna take big O of m, multiply by n, and this is actually n times m. Now, when dealing with graphs and graphs algorithms, we almost always use amortized time complexity, and as I explained you in the drawing, we are looping over the edges starting from node, and in total, overall, we will loop over every single edge in this graph exactly once. So this is going to be in total a big O of m. We won't multiply this by this, but we will add them together. Very well, this is constant, 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 and everything else is constant. So the time complexity is indeed big O of n plus m, and the extra space, as I've told you, oh, we also use the adjacency list. Okay, this is also extra space indeed. We have the queue and items, minimum dist and items, and the adjacency list m items, the number of edges. So the extra space will also be big O of n plus m. And this is the BFS. As I've told you, please remember, the BFS is an algorithm that is designed to solve problems like this one involving minimum paths, minimum distances between nodes, instead of just traversing the nodes and see some connected components, or if some node is only reachable from another node. That's a DFS algorithm.